Hello, my name is Ben Rinehart, and today I'll be presenting on data mining techniques and how they are applied in the clinical healthcare field. So first, a little motivation behind this. Currently, there's large amounts of physiological and biological data that are being captured and recorded in the healthcare field, which is large clinical databases of data which could be analyzed, but currently the use of this information is pretty limited beyond standard archiving methods and is drawn back to on a case-by-case basis. So I think there's great potential here to apply some data mining techniques to these data sets, which could possibly increase healthcare diagnostics and effectiveness moving forward. So today we'll look at some examples of this at work. The first is an automated DICOM database. So this is in response to the U.S. national press actually raising concerns about the amount of radiation used in clinical diagnostics, both that the radiation is not being properly subscribed and the exposure levels are not being accurately monitored. So they came up with what they're calling the DICOM Index Tracker, or DIT, which serves to record, monitor, and provide automatic alerts of radiation levels. So this captures desired data from DICOM takes for CT scans, it covers mammography, angiography, and other common types of CT procedures. And the main function is to send a notification to either the physician or other healthcare provider when these radiation doses are exceeded, either for a single procedure, a single patient, or the same procedure repeatedly. So they targeted 4 parameters: the procedure time, the max voltage setting of the radiation source, the max exposure seen by the patient, and then also the type of procedure, which was a classification. So the first 3 parameters are measured and compared against the threshold values, and then if exceeded, a notification is sent to the specified recipient. So after this data is checked, they actually put it into a database, and that's when the data mine can be applied. They apply regression analysis, which can be used to check trends between max exposure and procedure length, and then these 2 parameters can be checked against the type of procedure to determine if it's happening repeatedly in the same procedure, and then a decision tree can be used as a predictive model to determine which procedures are at risk or for exceeding radiation levels. So that's just to show an example of how data mining could be used to analyze common data that is already collected. So the second is a cost-effectiveness study aimed at pediatric appendicitis. So pediatric appendicitis is the leading cause of surgical emergency in children, and there's 3 types of screening that they can use: ultrasound, computed tomography, or ultrasound plus computed tomography. And they want to determine or develop a decision-making model that takes into account the risk of radiation as well to determine which screening method is the most effective. So they used a Markov decision model, which is a mathematical framework which where decision-making outcomes, they're partially random. So you take into account 4 components. There's a set of real-world states, a set of possible actions, a quantifiable reward function based on the action you chose, and a description on how each action affects each state. There is an assumption here that each action depends only on the current state and not prior history, which I think is a fair assumption for these screenings because they don't take into account prior visits, just the current screening that's being used. So they use real-world data to generate the decision tree for this model. Data have 3 classifiers as before: ultrasound CT or ultrasound plus CT, and the results of each screening technique led to either appendectomy or discharge classifier for the patient. So screening specificity and sensitivity were used to determine effectiveness, and in this graph on the table on the right, you can see the average cost and also the average effectiveness for each type of screening. On average, ultrasound was the cheapest and the least effective strategy, where ultrasound plus CT was the most effective, but also the most costly, as you could imagine. And CT fell in between for cost and effectiveness. Incremental cost effectiveness analysis was used to determine the most efficient method. This is a measure of how much additional money is required to gain additional outcomes. So a procedure is deemed effective if the willingness to pay threshold, if it's below the willingness to pay threshold, which is usually set around $50,000 for these procedures. When compared all against each other, actually all of them fell below the threshold. So that means the most effective way to do it, cost-effective rather, is to choose the cheapest screening first and then use more expensive screenings if the first screening comes back as a negative. So first do an ultrasound, then do a CT if a negative ultrasound is returned. The next study we're looking at is enhancing patient safety through automated data mining of nuclear medicine reports. And this is they're wanting to develop an open source toolkit actually for creating exposure data archives and repositories from existing archives. So they want to demonstrate the potential applications of this toolkit. So the first application was measuring exposure variation. So they looked at a data set of fluorodeoxyglucose administration levels. And they wanted to look at this because recently the FDA actually lowered the amount of acceptable administration of this drug. So they broke up the data into 3 time blocks versus all the data, then 6 months before the change in protocol, and then 6 months after. They used an extraction code to train on the first, or they trained an extraction code on the first 1,500 reports in the data set. They're looking for a unit of radioactivity at quantitative measure, and then the type of radioactive agent being used. And then they actually manually reviewed 150 of these reports to make sure that the training code is working correctly. After they trained the algorithm, the entire data set was mined for these fluorodeoxyglucose values, and there is a sharp decrease shown in FDG administration at all levels after the protocol is lowered, which makes sense. That means they're following the protocol. So this just demonstrates how you can effectively data mine an entire data set to see if protocols are being followed, to see if thresholds are being broken, things like that. They also did the same thing for radiation levels. So radiation exposure was extracted in the same way, and they actually used a decision tree to classify where the radiation was being administered and the amount of exposure that was being used. And then a heat map was used to show radiation doses across several different organs, which are on the y-axis, time is on the x-axis, and then the color of the heat map is how much radiation was used, with red being more radiation. The next is predicting breast cancer survivability. They wanted to take advantage of recent advances in medical imaging to develop a better predictive model for breast cancer survivability and prognostics. So they compared 3 different methods of data mining and predictive model creation: artificial neural networks, decision trees, and logistic regression. So the prognostic factors being used were both chronological and biological, and they actually analyzed an SEER database which contained over 430,000 cases, and each case had a binary class variable, which was 1 survived or 0 did not survive. So the data needed to be prepared before it could be analyzed. There was a lot of cases where the death of the subject was due to something other than breast cancer, so they removed these cases. And also before 1988, a lot of cases had variables missing because there wasn't a standardized method of reporting these values. So they removed those cases as well because they didn't want to skew the data. And on the right, this is just showing how that affected the age distribution. I actually concentrated the age more along the center line when they removed some of the data. Here's an example of the artificial neural network that they created. These neural networks are capable of modeling complex nonlinear functions, which is important in a case like this with all these variables. There's bound to be some that aren't linearly related, so it's good that it can model nonlinear relationships. They utilize a multi-layer perceptron learning algorithm and then backpropagation for training, which is where they calculate data loss for each node in the network and then change the order of the nodes to minimize data loss. For the decision tree, they use a similar method, which was entropy-based information gain for splitting the tree. So this is where each observation for a decision tree is split into 2 or more subgroups based on the highest information gain. So you continue until no more splitting can occur, or until no more information is gained, and the order of the decision tree is changed until the highest information gain is achieved. So the third model was logistic regression, which is a generalized form of linear regression, and this is when a model is built to predict the odds for an occurrence, and if the odds are above 50%, then they're giving the survived qualifier. However, this assumes a linear relationship between all the variables. So to determine the best classification order, particularly for the decision tree, they use a tenfold cross-validation algorithm, which is when 10 subsets of the data are analyzed and then averaged. So you get 3 measures for each modeling technique. We're looking at accuracy, sensitivity, and specificity, where sensitivity is the true positive rate and specificity is the true negative rate. So here's some of the results on the table. You can see the measures for each type of modeling. The decision tree performed the best, followed by the neural network, and then lastly the logistic regression. And on the right, we can see the impact factor of actually each variable analyzed in the study. So this is just showing how much of an impact each variable had on the prediction results. So things like grade of the tumor, the number of tumors, the stage of the cancer, and radiation used were obviously the most impact. So the next study is intelligent heart disease prediction. They're using data mining techniques to predict the onset of heart diseases. So the factors here include age, sex, longitudinal physiological measurements like blood pressure, blood sugar, heart rate, and then family history. This is a really good example of what we were talking about earlier, how there's a large database of measures that are already collected. Like when you go get a checkup, you get your blood pressure taken, your heart rate, you get your blood sugar taken sometimes, especially if you have diabetes. So this data is already out there, so they're just looking at a way to data mine it and get some positive results out of it. So they're evaluating 3 models: a decision tree, a neural network, and a naive Bayes rule, which adjusts the variable weighting by calculating correlation between dependent and independent variables, and then reorganizes the order of analysis. So here are some of the results shown in a lift chart. So on this lift chart, the blue line here is a random guess algorithm. So that's just if you would randomly guess if a person is at risk or not, that's how often you get it right. On the x-axis is the overall population used to train the data. On the y-axis is the amount, the percentage that you're correctly saying have heart disease of the people who do have heart disease. So the ideal line actually only uses 46% of the data to capture 100% of the correct cases, and that's the green line here. The purple line is the neural network, yellow is the naive Bayes rule, and red is the decision tree. So here's the evaluation. The naive Bayes rule actually outperforms slightly better than the neural network, with both vastly outperforming the decision tree. As you can see, that red line lagging behind, particularly as more population is being used. So the next study was data mining for detection of high-risk breast cancer groups. A decision tree was applied to detect joint effects caused by single nucleotide polymorphisms occurring in multiple genes at the same time. And so this SNPs is the most common type of genetic mutation. That's when a single nucleotide is actually replaced with one of the other 3 possible nucleotides. And these genetic mutations can actually be measured, evaluated, and analyzed. So they want to determine a classifier that maximizes specificity and minimizes false positives. By having this focus, they're actually going to have a lot of false negatives. They're going to miss a lot of people who are at high risk. But since labeling a case as high risk can drastically change lifestyle and medical habits, they want to focus on minimizing the stress which could be caused by false positives. So they didn't want to tell somebody that they were at high risk unless they were sure that they were. So they wanted high specificity for that. On the right here, you can see a model of their decision tree. This is one leaflet of decision tree where alcohol is the main risk factor. And then in the ovals branching off of alcohol, you can see the actual different genes with their specific gene name. And then off each gene is a branch of the nucleotides present in that gene. So that's the possible nucleotides that are present. And then that's either branched into a different gene or branched into a high risk or not high risk group. They use a Fisher extract test to determine the associations between 2 variables, and then a tenfold cross-validation to determine the best leaf configuration. So they did this actually 1,000 iterations to improve the tree, and the lowest FET ended up being 9.7 times 10 to the negative 6, which shows a very high association for this tree. So look at some comparisons between this study. Of the studies evaluated, 3 of them focused on developing predictive models, and all 3 employed a decision tree technique, which shows that decision trees are widely accepted and commonly used for predictive modeling. 2 of them focused on comparing techniques. Both compared neural networks to decision trees, and then the third technique was different between the 2. One used naive Bayes and one used logistic regression. So I wanted to compare the naive Bayes and the logistic regression. Naive Bayes was used in heart disease prediction and was one of the best predictors used. And this is actually a family of algorithms that assumes particular trends in one variable are independent of those in another variable. So it's not assuming linear relationships, it's just assuming that the trends are not related, which might not be a suitable assumption for medical diagnostics and predictions. However, it's better than the assumption that's used in logistic regression, which assumes that relationships between input and output variables are linear, or input and classification variables are linear, which is definitely not the case in medical diagnostics, which is why I think logistic regression performed pretty bad in the breast cancer survivability study. So looking more at the decision trees that were used, all the predictive modeling studies use the decision tree as one of the main methods. For training and evaluation, both a Fisher extract test and entropy-based information game were used. Both are actually acceptable forms of decision tree building and evaluation. The data was broken into 10 subsets of the same size. For the tenfold cross-validation, the data is broken into 10 subsets of the same size. Training is done on 9 data sets and tested on the final one. And it's actually repeated 10 times, and the accuracy and specificity measurements are averaged. And this is a very accurate way of maximizing decision tree specificity, where you're doing a lot of training on different parts of the data set, which is really good. So just some overall takeaways. Decision trees seem like the most commonly used form of predictive modeling in the healthcare field, and also the most accurate. They're able to predict around 90% accuracy in some cases, which is very good compared to other healthcare standards. As healthcare databases become more common and increase in sophistication with the medical imaging techniques being used and the amount of data that they're collecting, I think it'll be very beneficial to apply data mining techniques to these data sets, which could vastly increase diagnostic, prognostic, and efficiency as a whole for disease prediction in these medical procedures. So here's the references. Thank you for your time, and thank you for the wonderful class this semester. Thank you.